Welcome. We now want to have a deeper look to the mechanics of the coding of architectural models. We will create a model like this, which is not exciting, but for didactical reasons it's quite okay. It will cover the topics I think important. It will show you how to turn the different aspects of coding towards very adequate towards architectural models. So the key idea is with coding that you don't have to do any redundant work. So any decision you're doing has a very specific place, and you don't have to put a decision at several locations. And then code is evolving it towards whatever you like. So this is the wireframe, this is the rendering, this is the logistics, this is calculations, or this is robotic control, whatever you like. It's always evolving toward that, but the nucleus or the code is very compact without redundancy if you're doing it well. Quite different to the drawing on CAD systems, where you have to do a lot of manual work, a lot of repetitions, and you have to change a lot if you change your decision. For example, recalibrate the grids or these kind of things, and you have to redraw, and you have a lot of manual work because it's redundant. And because I think architecture is not about the visual and it's not about geometry. It's about not Cartesian geometry in today's term. It's about talking about the building and making a poem as code. So now let's have a look how this works. So we distinguish between constituting the coordinates. So this is how to take space, put points in space. That's the first step. Then we go for topology, so we connect these points with edges and faces. These are the two next chapters. And then we make it real. So this is a kind of wireframe, the first things. This is just organizing space in the rational. We had the rational here. So in our last chapter, harmonics, we had the rational, which is the red points. So this is the first three chapters. Put everything in proportion in space. And then we go and in principle we get objects from a library, or we buy products on market and put them there. So therefore these objects, they have, I call it the dreams of the night, or they're product by rotating machines. They're produced by rotating machines overnight in the production hall. And then they are products. And these products are memories over time, so they're produced, and they are capsules of times or traces of times, or in contrast to architecture. Architecture is a red line. Blue is I think the design. So this is production, this is in the hall, and this is about time and optimization, simulation, producing, and so on, all these circular things. Take them, so in principle you buy them and put them to their place. So the columns, the beams, these nodes, the facade elements, and so on. This is, I would say, make the model real. So this is a rational setup, and this is to make it real. So therefore we looked at the harmonics here in this chapter. Good. Let's start. So as we had it with a starter, we simply have very few lines of numbers. We go in X. These are 5 X's, 1, 2, 3, 4, 5. Then we have in Y-axis we have 1 and a 4, so it's 1, and then length of 4 And in three and in Z direction we have 1, 2, 3, 4, 5, and we give that a certain proportion because our image here has a certain proportion, or a facade element. It's this. Then, as we did with the starter, we get these tuples, and these are our points. So this is how to constitute this space. And of course, we can pick each of this point and put it somewhere else, but this will be the next chapter in our series about complex geometry. So now we start with this super simple grid. First step of topology, we need to go abstract. So we say vertices, and this is just the number of points. So we have to assign a number to these things, an index. That's here. We simply say coordinates. We ask for the lengths, the amount of coordinates. These are 50. And then we make a range, so we put it to 50 elements. So that's the first thing. And now if we want to go for counting and for measuring, we render graphics with mesh regions in Mathematica. So, and here, these are the points in space. And then we can ask, for example, now this is assigned to R, and we can ask R, hello, mesh region, mesh cells of R, and then the 0 dimension, and then we get points from 1, points 50 points. So very simple. If we go for lines, this is the first dimension. We have none. We have faces, none, and we can have a lot, in principle, a lot of dimensions, no problem. Now we stop with 3 or 2, and that's it. We can go for the mesh coordinates. To give you an idea of how mesh coordinates of R. And this is a data structure which is optimized for measuring distances, countings, and so on. We will use it towards building information models and so on. So it's proper for that. It's not proper for good rendering and visuals. Good. So this is the first step. We can give other options, for example, if we set the options of mesh region, which is this renderer, and say we want to have the labels of dimension 0 as index. If we put that, then these are the numbers. We also can go for highlight mesh. We say point, so dimension 0, number 2, so this is this one here. We want to highlight this point, and then we go and see this is highlighted. So these are the principles to give an idea. Otherwise, you simply go here with all the detailed examples given with Mathematica. If you want to reset the labels, because it's disturbing if there are too many, simply say mesh region, mesh cells label, and reset it to nothing, and then this stuff here the renderer has other options, and now it's without. So very simple. This was with the vertices, just how to manage it. Having that, now we want to go to edges. And these edges, they are working, we can find them by the geometric Euclidean distance between the vertices. So the idea is using these distant metrics, which is having the Euclidean distance from each vertex to each other. You have to be careful because there is a massive explosion of combinatorics. So with these small models it's working. You will have it with a large model. You have to wait for some 20 seconds and it's exploding easily. So this should be done with more care and code if you go to large models. But for this small thing, it simply works. So you make the distance from each point to each one, and then we select just the length of one, which is what we need here. The diagonals, they are irrational in most cases. So we want to have this length of 3. This is from 1 to 4. That's the length of 3. We have to separate this 3 from a 3 here. So this point is connected with here on distance with 3. So, and we want to have this proportion here, this special proportion here, and we want to have that. So what we are doing in this function here, we get the distance matrix of all the coordinates, look it up. We have to be fast, so I can't explain that. So then we select just the one diagonal. We don't want to have point 1 with point 8, which is symmetric with point 8 to point 1. And we just take only half of the matrix to don't have these redundancies, because our edges here are unidirectional. So, and then we select the edges which are either 1 or our proportion or 3, and ask for them. So if we're doing this, then we see these are the edges which are either of this length or of this length. This is the or of this length. So you see cases on this data set, on this distant matrix. We ask for this structure. This is our key, either 1 or 3 or this proportion, looking at the matrix, which is constructed here. And then these points are in distance either of these 3. So here we look for the edges in the direction of y. So this was the problem here, toward here. So we're looking, position. It works similar to cases. We take all the coordinates of the edges. So we take the edges, we put the edges to the coordinates. So then we ask for coordinates point 1, point 2, and ask whether the Euclidean distance of point 1, point 2 equals 3, and point 1, point 2, point 1, point 2 second, so this is y, is equal. So if it is this, we get this position, and we delete all edges of this list, delete of this list all these positions to get the proper list. So this is a little smaller, and here we are. So these are our edges. And you see this is very generic. You put the points, and then you do the collection, and then you make filtering. It's a filter like we have it here. Here with our image, we make a certain filter, high pass, low pass filter, to get certain connections within space. And these are our vertices. We don't draw anything. We just filter and tune. So, and here now our mesh region is now with the same coordinates, is with the same vertices, and now we put line to edges. We want to see the edges as lines and do the same thing. And here we are with our grid. So now it's important to understand that we easily simply can put completely different proportions here or other numbers, and then all this works automatically and we instantly have another grid with the same tuning, with the same filters, and then we have a new grid. So again, we can go for the indexes. We can now label with the, because mesh region is for measuring and counting and addressing. So all the logistics things we need in building information models, it's here. So for example, we can go and say the labels, instead of O, we put it to 1 and say this is, we want to have the index. If we now see that now we have the numbers of the edges of and so on. So put that back again. Make that 0. Always very slow in the cloud. Now this is proper. Good. That's for the vertices, straightforward. That's for the edges, straightforward. Now the faces. And we need graphs for that. So a graph is a tool not for not for counting and measuring. It's a tool exactly the opposite. It's for connecting things. So running along axis and the connectivity of things. That's a graph. So if these mesh region is in geometry, because you see all the things in space and count them and get them and so on. Graph is topology. It's on the connectivity of things. So it has no form. So now you build it up in a very similar way to the mesh region graph. You go for the vertices. That's interesting, yeah. You don't start with the coordinates, you start with the vertices. Then we name it not, the edge is not a line, but an edge, undirected edge, which has no coordinates, but like we had it, just numbers of vertices to connect. So it's a mesh, you can put it in any form. And in our case, we now put that to be in sync, but this is optional. We put that to the vertex coordinates and to put that to our coordinates, so not to be confused, to find them. We have labels, size, and so on, all this to make it a little more attractive. So this is not important. So now this is the connectivity of things. So it's not the objectivity of things. So this is the subjectivity of things. And this was the objectivity of things. So here we are. We have all the vertices, we have indexes to the vertices, we have the edges and so on. And for reasons of pragmatism, we simply put our coordinates so that the graph looks the same like a mesh region. Now, what can we do with graphs? For example, now it's about neighborhoods. It's not about identifying. We simply, for example, ask neighborhood graph of graph 1. This is here, and then we can say 2 of this graph. And then we have 1, and then we get the neighbors of it in S1. So here you see. Here, the neighbors of the graph. You can work like this. Or you can ask, what is the shortest path in the graph from 1 to 50? So tell me one shortest path. Then he says, you can go here and then you're from 1 to 50. So this is what graphs can do. Or we can, here these are, we said, no, we don't need that. So, and now, for example, and this is why, because all the internet is a graph. And then you can find the important points, the centrality of points. So, and list that between graphs. So it's something like the distance matrix. So we get the distances of the vertices crisscross. And in this case, we get the importance of elements. So central elements are now, they are, so because they are neighbor to important neighbors. So, and this is how they measure the internet, the important pages, because they're connected to other important cases and pages. So all this can be done with graphs. Just to get an idea, look it up. So what we are doing with graphs is very simple. We try to find the faces. So, and therefore we first we select a subgraph. And we simply say we just want to concentrate on the, I leave that, we want to concentrate on these planes, on the vertices and edges of the front. This is done by this, we say subgraph, graph, of graph, and then we say position of, we just take the coordinates where this I can show you how it works. It's very important to have these keys always. So these are our coordinates, our 50 coordinates, and then we say this is our key, and we say coordinates are always x, y, and z. So we say whatever x is, if y is 1, whatever z is, on the level in the hierarchies in coordinates 1, we can put it older than slower. So then give these positions. And then they say in the list of coordinates at position 1, 2, 3, here, 45, 40, 44, these are positions of y, where y is 1. So which means you flatten that and make a subgraph. So if we flatten that, you see this here. Get rid of all the sublists. These are the points, the coordinates of this facade. And the subgraph then is taking just these coordinates. And if we look at it, then we have exactly the same numbering as in our graph, but y is only 1. Very simple to do. So if we have this facade, then we can go for a find cycle. So what we want to have is find cycle. I'll go here. Exactly of 4. So because it's always a face with 4 edges you want to have. We don't want to have bigger ones, just these cycles. Exactly, therefore we don't want to have up to 4. This would be like this. This is exactly 4. And we want to have not only 1, we want to have all of the cycles. And then he says the undirected edge of 32 to 35, 35, 45, 45 up, and 4, this is a cycle. And there are more cycles of them. So now we don't want to have, I think, all these. So this is what it is doing. It just takes off all the first element, and by that we get these lines, what we need for bases, 34, 35, 45, 44, and that's it. So if you put that here, you see these are the faces. So this is what we can do with graphs. Very, very interesting to connect things and, for example, to create the faces. So leave that. And therefore, faces of the facade. There might be, there are some crazy things. For example, you can make a 4 times thing. This is what they find now is, if you have, of course, you can have faces like this, 1, 2, 3, 4. So this here. Or you can have 1, 2, 3, 4. These lines. So, and to get rid of that, we check all the faces towards the area we are looking for. We simply say it should not be 0, the area. For that, we use this area. We make a polygon, which is a region, a mesh region, and check the mesh, measure the mesh region of all these lists, and we select it. So this, in sometimes, is necessary. Normally, it should not be like that. So this is a safety function. So therefore, we can ask how many functions facades are there. 16, and this is 16. These are the faces. So very simple as well. And that's it. Using the graphs for the faces. Render it again as a summary. Now we go for the indexes of the mesh region and say the faces should have the indexes, have the points, lines with edges, polygons with facade. And then the synchronicity of this is important. So that's it. So the mesh cells sync is I wrote this function. It's a little tricky. So because you can have a cycle like this or like this, and or you can start at the lower left and then go up, or you can start at the upper right and then go like this. And with that, I always put it clockwise, and I always put it lower left as a starter. And it's running like this, that you put any kind of mesh region, and then you take a sample, this is in this case 1, and say all the others should be of the same orientation and the same adjustment. So it's always orientation, and it's the same phase, because these are all turning rotations, the same phase as the sample. In this case, we reference it to the 1, and then all the others are of the same kind. So this is always a very big problem in CAD systems, to make that proper with your faces. So, and now of course I can, for example, say highlight face number 1, like we did it with the point. And here we are. We can go for face number 3. Good. Okay, now we finish the topology. So this in principle is our architectural model. And this corresponds to the red thing here. And now we are go shopping. for products to realize our abstract understanding of how to proportion space, to bring space into proportion. Go, last chapter. So using for that the third render engine. So we had the graphs for the connectivity. We had, so what this was connectivity or the subjectivity of things. We have the mesh region for counting and measuring. So this is the objectivity of things. And now we have the graphics or graphics 3D. Graphics is for 2D. 3D to go for the visuals, to go for the reality things. And again, with the graph, we have a graph complex, so which is very convenient because it works exactly like the mesh region. We say this is, we start with the coordinates, then we say we want to have the points on the vertices in red. We want to have gray lines for the edges and white, half opacity polygons for the faces. Then we want lighting, neutral boxes, faces, and so on. So then we get a properly rendered 3D object of the ratio of our building. This is our architecture model. This corresponds to the red. Now, we go to BIM, we go shopping, and we have to buy the vertices. So these are nodes, connectors for the construction. So for simplicity, we simply make a box for it. So this is how it works. The vertices are in our, we can get the parts of the mesh region. We get all the parts of the mesh region, so this is 0. We get all of them and simply say, okay, these are 50 nodes. So we have that. So now we have to buy 50 elements. The elements, we call that VO, vertex 01. So in this case, to simplify that, we can do any kind of complexity. So this is a designed object, a product. In our case, we simply say it should be gray, it should be a cuboid, and the insertion point should be minus a little, plus a little, minus a little, and then we have a cuboid, wherever it is on the locations of these vertices. So this is our graphical element in the library of the product. We can have a production number and so on. So then we made a table. So it's a list of attributes towards all the vertices. So in our case, this is a part. We say it's a part, and this representation, and we can add it like columns in a spreadsheet. We can add the article, the price. We can add whatever you like. So in this case, just the part to make it simple, and we make that for all this here. We made that for all the elements, mesh cell count, range, and so on. And then we get the shopping list. Very simple. 50 elements, they're all of the same, and so on. So, to access this data set, this table, it's very simple. Part number 1, attribute part. So the first vertex attribute part, and then we get V1. So if you want to see what is there, because this is a symbol, this is a string, we have to say to expression. And then we ask, for example, here. So this is a little so we can simplify that, but I think I want to show that in detail. So if we want to get that at a certain location, so we need the coordinates of that as well, of the vertices. Then we say this is a gray cuboid at these special coordinates. If we go to the 12th one, so I have 50 of them, then we know where to put it. So the interesting is that this graphics with this pure function here is parametric. So, yeah, and it's parameterized with the vertex and the coordinates of, so the vertex, and then the coordinates of this vertex, and then put it into this element, apply the coordinates, and so on. So look it up, try to understand it. There are other tutorials to make that in detail. So that's it. So this is very generic. So this is just to show how this works. This is, you don't need that because this is, so you can just, it's just directly there with the mesh cells. So what we need is a part, and we need the data set for the parts, the shopping list with all the attributes. And then you go for the generic graphics. This is generic as well. You never have to change it, but this is now putting all these products to these rational points to make it real. So to make it in between, to make it sound like. So, very simple. It's not, yeah, it's a little tricky to do and make it here in syntax, but it's always the same. So just copy it. Now the same with the edges. We have all the edges of the mesh. It's dimensional 1. Then we have two different parts. We have a cubit. So this is for the beams. It works like we had it with the nodes. We have to. The problem here is that we don't know whether it's left, right, left. So we don't know from which side it is. Therefore, the addition and the subtraction here for the difference, it's not clear. Therefore, we have to organize it and normalize it in orientation here. This is a little more complicated, but then there's a cuboid, and then for the verticals we need the cylinder. So two elements to buy. We put the edges and see these are the edges. So, and now we make a data set of, we take all the primitives of the lines. The primitives are, in comparison to the cells, the primitives don't give the index of the vertices, but the coordinates of these elements. So that's directly with the coordinates. And then we say if, and now we have, this is again a key, if there is a line, so we can ask for mesh primitives here, you see what it is, how it is working. Mesh primitives, 1 in the first element, it's like this. So it's a line, and then the 12th element is another line. If we go to the area, this is a polygon as we made, is one of our face. If we go to 0, then we have a point. As we set up the mesh region. So therefore we can ask for line, whatever x, y, and z is. The second point should be whatever it is in x and y, but it should be the same like here. And then it should be C1, which is the cubit. So therefore z is equal, so it's the same, so we want to have a beam. So if Z1 here, 2 here, and Z1 is unequal Z2, then make it a cylinder, so which means it's a vertical. So very simple, and make a data set of it. Automatic. First is a beam, column, beam, and so on. 100, 105 of them. This is what we have to buy. Again, the renderer. Now it's not only the vertices, we also have the edges, and the function to do that is very similar to this. Don't do it, and here we are. Very simple. And you see these are parametric objects because we have variables here and we put them to our system. We get the coordinates of the mesh cells and we put that to graphics, and we parameterize these elements. Nice. So last is the faces. And here, this is just to make a recap. The coordinates, because it's too much work always to collect all these symbols in a fresh way. So I make a collection here, coordinates, vertices, edges, as we did, the faces. So, and then this is interesting now. We want to have the normals. So which is the normal to the faces, and to get these two functions are to create normals, because we want to have an offset of the facade from the grid along the normal. This is done here, so we call it F faces normals, and if we make that, we are here. Now we have an image. We take this facade of Wagner in Vienna, and this is one of the temper of the facade. This is a temper image. So take that. We have it very small, so that we can do it on in the cloud, make it high resolution if you go on the desktop. Now here, facade 01. This is a polygon. We take its texture and we can look it up how it works. It's just a parametric object with texture. So, and now again the data set again is very simple. We have 16 of them and they are all of F01. So graphics again, it's even simpler here. It's the graphics, and if we go here, we are with our faces. Got them in place. So we used the normals here, polygon plus as a parameter, and we need the normals of this element to make an offset in to make an offset in alongside. So we had the coordinates here of the polygon, and we need 0.1 units along. The normal is going out, therefore the facade is in front of. If we put that to 0, there's no offset. So just have this. Everything else is okay. Then it's within. So normals are this direction, and we need an offset. So everything is very nice and properly done. Here we are. Good. That's it. Very strict, very clear. You have to make this distinction between the architectural model. Therefore, it's so important what I said here. So within the architectural model, and then the designed objects, and you have to combine both with tables. So, and the architectural model itself uses for the objectivity of things the mesh regions. You can count and measure in space, and the connectivity of things, you need the graphs and this is the subjectivity. So the connects of things, of your model. And if you combine that, it's always about spaces. So I've got connections, and if the calculus, you have the keys you can manipulate, and by that you develop. Then you go with a 0, 1, 2, and maybe a third dimension if you want to cover the entity of spaces. Combine that, and it's in all buildings like that. So we will follow up with a large model. We don't want to go into details here, but I can show you that if you have the principle, it's an abstraction of the size of buildings. That's very important. So you don't have more work if the building gets bigger. It only have more work if the various things get bigger. And therefore, the next tutorial will be about how to go with irregular geometry. So that's it. Thanks for watching. See you.